Having determined the principles of setting hypotheses, the next stage is to examine the statistics used in hypothesis testing. This will be about testing the significance of relationships explored. We will be looking at measuring the strength of these associations later on in the module series. There are many different tests that we can use to test the significance of relationships. The choice of which statistical test to use depends on the data type, the number of samples we have, if we have two or more samples, whether these samples are independent or dependent, and the type of data that we're dealing with, i.e. whether it's parametric or non-parametric. In the previous slide we said that one of the things we need to know when choosing a statistical test was the number of samples we are dealing with. What do we mean by this? If we say that we are looking at the average salt content of breakfast cereals, or the average income of women aged between 18 and 25, or the average number of times men aged 18 go to the cinema, we would be dealing with one sample. So we are comparing our sample statistic with a specified population parameter. We're just looking at how our sample compares with the true population. However, if we wanted to know whether the number of visits to a cinema was different for men aged 18 and women aged 18, then we would be dealing with two samples, one of men and one of women, and a summary statistic can be calculated for each, i.e. the number of visits to the cinema. In this slide series we are going to look at one sample tests, and the following slide series are going to deal with situations where there are two or even more samples. In particular, we're going to look at one sample test for parametric data types. In the next part 2b, we are going to deal with one sample test for non-parametric data types. Following that, we are going to move on and actually start working with two samples or more than two samples. Before exploring the types of hypothesis tests, it's useful at this stage to talk about what we mean by one-tailed and two-tailed hypothesis testing. Hypothesis testing is divided into one-tailed and two-tailed tests. The difference between them is that one-tailed tests impose a specific direction on the alternative hypothesis and two-tailed do not. For example, in a one-tailed test, H1, or our alternative hypothesis, H1, is that men visit the cinema more than women. In a two-tailed test, our alternative hypothesis, H1, is that there is a difference in the number of times men and women go to the cinema, but we are not expressing a direction whether that difference is more or less. For both H0, or our null hypothesis, would be that there is no difference in the number of cinema visits for men and women. Now, if we're going to go about using one-tailed tests, so when we're actually specifying a particular direction for that difference to happen, a researcher really must have very, very good evidence to do this, as if the direction chosen is incorrect, so if we take that example and we say that men visit the cinema more than women, when actually the outcome really is that women visit the cinema more than men, it leads us to falsely accept the null hypothesis. The majority of time a direction can't be assumed, so we generally focus on using two-tailed tests rather than one. So thinking about hypothesis tests, we're going to start off looking at z-tests. So if you know the standard deviation and the population mean of the true population, then a z-test can be used to examine how different the sample mean is from the population mean. This is often seen in medical research in, say, for example, examining bone density, body mass index, or the white blood cell count of a sample of people. In the case with examples such as bone density, BMI, and white blood cell count, there is an accepted definition of the average for the whole population. You can then use a z-test to compare one person's bone density to the average values for a person of that same age and gender. With an accepted definition of the true population, your data is compared against it to see how close or far away you are from the average for someone that is the same age and the same gender. As the true population is known, it is also then possible to know the standard deviation for the true population and thus the standard area, and so we end up being in business. Now, going back to the earlier lecture on hypothesis testing, to distinguish whether our sample is indeed part of the defined population we think, whether it is actually part of something else, we have to calculate our standard error. The smaller the value of the standard error of the mean, the better our sample population mean is as an estimate of the population mean. Now, of course, to do this, we need to know the standard deviation of the true population. The z-test utilises the standard error, as we can see in the equation, and here x bar is the mean of our sample minus the population mean divided by the standard error of the mean derived from the standard error equation. In our examples of bone density or BMI or white blood cell count, accepted averages are known for the population at large. Therefore, we can know the standard deviation and we can proceed with the calculations using this information and the information we have gathered from our sample. However, this is, of course, the Achilles heel of the z-test, is that it requires more information than is usually available. As we talked about before, it's very unusual for us to know the standard deviation of our population. So if we don't know the standard deviation of the population at large, we can't calculate the standard error, and then we can't use z-scores. In the majority of social research, we don't know what the standard deviation of the true population is, and so we can't calculate standard error. If we don't know the standard deviation of the true population and we can't use a z-test, we actually use something different. We use what we call a t-test. So here we're going to have a look at the alternative, which is what we call a one-sample t-test. Now, a t-test uses the standard deviation of the sample to estimate the population standard deviation, so we work from the other way round. With the t-test, you compare the sample mean to the population mean and get an estimate of the probability that the sample mean is different by chance. We use a one-sample t-test in situations where we are dealing with one sample and our data is parametric. We know or can estimate the population mean, but we do not know the standard deviation of the population. In this kind of situation, the test for significance depends on a slightly different sampling distribution from the normal one, and we call this a t-distribution. And you can see here on this graphic the equation for the t-distribution, for the t-test, and you can see that basically the t-test is your observed mean minus your expected mean, and you divide that by your standard deviation over the square root of the number of observations less 1. So let's have a look at an example of a one-sample t-test. We want to know if the average number of visits per year to a particular cinema is different from a claim by a rival cinema of an average of 20 visits per year. Because we do not measure, we will not measure every visit to the cinema in the population. We can't go and ask every single person in the whole population how many times they go to cinema. We will not know the true value of the population mean and therefore standard deviation and standard error. Therefore, we end up using the t-test. The hypothesis is that either the sample mean is equal to 20 or it's not. So HO, our null hypothesis, is that the sample mean is equal to 20. H1, or alternative hypothesis, is the sample mean does not equal 20. Our sample generates, our sample of 75 people generates a mean of 18 and a standard deviation of 9. We set a hypothesis testing criterion of 0.05, so that's at the 95% level. We use a one-tailed test, as the equation denotes, that either the sample mean does or does not equal the population mean. So using the t-test statistic that we know from the previous slide, the value of n-1, so the bit at the bottom, that's circled in red, that actually gives us our degrees of freedom. In this case we are 75. We've interviewed 75, we've surveyed 75 people, so we have 75 minus 1. The curve for sample sizes above 100 are indistinguishable from the normal curve, which is why a normal curve can often be used for larger samples, rather than having to use other forms of testing. We can actually, if the sample sizes are big enough, we can actually move back over to those which deal with a normal curve. Below 100, the shapes of the t-distribution are given in statistical tables according to the sample size minus 1. The value of this is what we call the degrees of freedom. Here this equals 74. So looking up the critical value, so having plugged everything in, we get a degrees of freedom of 74, so 75 minus 1, and we get a t-value of minus 1.9. So we look this up in our t-table. We look up under the degrees of freedom, and we have a look at what critical value that gives us. And the critical value that the t-table generates for us is 1.671. So what we can say is that the t-statistic that we've generated from our equation of minus 1.9, okay, exceeds the critical value, so it's bigger than the critical value of minus 1.671. Therefore, if it exceeds it, that means that we have to reject the null hypothesis, and we have to conclude that the average number of visits to the cinema is statistically significantly lower than 20. So we can then write that t equals minus 1.90, p-value at less than 0.05.